Hey guys, welcome back to the channel. In this video, we are going to be deriving the Navier-Stokes equation. So I'm initially going to do it in the x component and just, I'm only going to do it in the x component and then we'll just replace that with the y component. So the Navier-Stokes equation is essentially just force is equal to mass times acceleration. Um, but mass is going to be in terms of density. And acceleration, we're just going to have it as the total derivative of velocity. Okay, and our forces are going to be your body force and your surface forces, like stress. Okay, so I'll just denote stress with the sigma. And if you remember earlier, in my previous videos, we derived the pressure static equation, and that was pretty close to the Navier-Stokes equation, except we have these viscous stresses. And so let's take a look at this cube. I'm going to draw out a little axis here and draw the cube along the axis. Okay, this is your x, this is your y, and this is your z. Okay, and this cube is going to have a length of dy, a width of dx, and a height of dz. So our forces that are going to be acting on here is going to be our body forces, which could be like gravity, as well as our stresses. So let's take a look at how our stresses are going to look. So we'll have pressure, which goes inwards at these points. We'll have right here, pressure. And in order to put pressure as a force, we need to multiply it by the area. So the area in this case is going to be dy dz. Now we're going to again use the Taylor series expansion to approximate pressure here, which is negative P plus, we'll have partial P, and since we're moving in the x direction, we have pressure x dx times dy dz. Alright, so that's pressure. And our stresses in the x direction are we're going to have a viscous normal stress. Now, this is not pressure, this is another normal stress which arises from viscosity. So that will be denoted using tau xx, and that points out, it points normal to our surface. So we're again going to do the same thing, and see how this one's going backwards, so we'll denote it negative. This one will be tau xx over e, and then moving x direction, and dx, dy, dt, I should specify that here too, sorry, dy, dz. Now, that's our normal stresses right here, but we have our shear stresses. So our shear stress in the x direction will have on the y plane in the x direction, as well as in the z plane in the x direction. So now this one can be denoted as tau zx, where z denotes our plane and x denotes our direction. And y, same thing here. We'll have tau y x. Okay? Now to make this a little easier, I should actually flip the direction of these over here, but remember they'll also be on the other side, that other direction. Okay, that's the shear. So for tau yx, essentially we're doing the same thing. We'll have negative tau yx, and the surface it acts on is dx and d2 plus tau yx. And we're moving along that y plane, so, or sorry, along the y-axis, dy, dx, dz. Okay, and now we're also going to have the z, zx, that's going to be negative 2x, that's going to be on dy dx and dx space. So if you see that, this is our x, and this is our y. So dy, dx, z, so zx plus partial now dx, and we're traveling along this plane. Here, dz, and dy dx. So now let's quickly do our little additions. So if you remember this p are going to cancel out. And in this scenario, this, this, and this are going to cancel out. So we can also take that dy dz, take that out, multiply by that dx, and we'll have negative partial p over x dx dy dz. Over here, do the same thing. We'll have, oh, sorry, forgot about this one. There's one. Now, perfect. That's okay. We have dx dy dz plus I need to go for that replacement. X over. Oh, did I write? Sure, sorry, that should be. And y dx dy dz. And the last this is term for here plus partial partial gx z, right? Dx dy z. Now that we are taking now that we're going to take a look at this, um, let's thoroughly go into and see what other reductions we can make. So right here, tau xx, these are, so pressure is already in the final form that it can be in, but our viscous terms, we have what's called the Stokes hypothesis, and I'll write that down right here. Stokes hypothesis. And in this case, our viscous moment is equal to 2 times mu, and this is the coefficient for viscosity, du over dx minus 2 over 3 multiplied by mu, and we're going to have the gradient of velocity, or actually we're going to have the divergence of velocity, sorry. Alright, so if you take a look at this, this right here is the same thing as, because this is simply just this is, so you get what I'm saying. So this right here is called the divergence of velocity. Now for this essentially tells us if we have any sinks or any outlets for our velocity. And when we take incompressible flow, this is actually, we're going to be taking incompressible flow, then this term is actually just 0, because this tells us where's my fluid sponge out. So you can just take that out, and this applies. We'll have this in y is equal to dx. We take that out. Oh, sorry, d over dy, and dc is equal to 2 mu, partial W over partial Z. Okay, so the Stokes hypothesis tells us that these are what we can plug in for our normal viscous stresses. Now our shear, um, we'll go ahead and plug that in. So a really important concept is the stress matrix. So the stress matrix is just a matrix of our stresses, just like it sounds, but there's one important thing about the stress matrix. And I'm going to construct that stress matrix right here. Um, see, and YZ. So what this tells us is that stress is symmetrical. Stress, that means that Txy and Tyx are the same thing. Tcx, Tx are the same thing. So T tau, tau, Yx is equal to tau xy. So this matrix A, the stress matrix, is equal to, so symmetrical, or it's equal to itself with the threshold. So the formula for this using the Stokes hypothesis is partial dv over dx plus partial dv over dy and zy are equal to yz is equal to w over. So an easy way to help you memorize this is we're taking the velocity in the z direction and that over y plus the velocity in the y direction over z. The last one is going to be uh, z, which is equal to x, which is equal to mu naught mu right now that we have these, let's go ahead and plug them in. I'm going to start with the uh, partial of tau xx. That's 2 mu du over dx. So we'll take out this, and we'll have 2 mu du over dx. Okay, and we're going to add partial y and tau yx um, Stokes, the Stokes hypothesis. We know that's going to be mu, mu over dx plus dv. Sorry, this should be dv over du over dy plus q. That's going to be um, q is plus u x. Let's see what we can do here. We distribute this out, and we can take this out, the 2 mu, because it's just a constant, right? I'm going to take mu out the whole thing, plus y. Okay, so now we're left with this, and we're almost at our final form for our equation for viscosity. So now what we can do is, you see these, this 2 means that uh, the second derivative can be added to itself, right? This 2 just equals this plus itself, right? So we're going to take that, this second, I'm making a little note on the side here to get rid of some of these extra terms, and I'll show you how we get rid of them. So dx equals 2. And now I'm also going to add to this second term, these additional terms that we had. Okay, and now I'm going to take out this, factor out this, and we'll get um, over here we should get d u over uh, sorry, this should be squared. Du over dx du over dy. You guys remember just a second ago something was going on over here, right? We're dealing with incompressible flow. I'm just gonna get rid of that. And that takes out this, oh, that. Oops, okay. I guess I cannot undo that for some reason with Microsoft. Get rid of that. And get rid of that. Not this, not this. Okay. Microsoft is being not cooperative with me. And you saw how you got rid of that. So Microsoft is not being cooperative with me, so fortunately, this looks like it's crossed out, and it's not. And putting everything together, I know everything's a little all over the place, but I do our best to put it together. So we've got this, and I'm going to shorten this whole dx action. I'll leave it up there. Dx dy dz plus, now we're going to have now these are all the surface forces, and we'll have our dx dy dz. We're also going to have our body forces, which I'm going to denote with F. Okay? And then we frame this in terms of uh, density. Okay. Now the left part of the equation, which is turning mass acceleration into terms of density and derivative velocity. So we have our density here, and then we're going to take a look at velocity in this x component, and that's a function. You know that velocity is a function of time. So x must also be a function of time. And if you remember from my other video where we briefly went over, or I didn't really go over it, but I made that little PowerPoint explanation. Hopefully it gets you guys to understand this concept of the chain rule. So I'm just going to go ahead and go over that. So du over dx, dx over dt. We're just breaking this apart using a chain rule. Du over dy, dy over dt plus du over dt dc over dt plus, let me just, so now we can also have gx, dy, dz, and yeah, that's it. That's another substituted for one component. You can just ignore all that. Let's look at the beautiful picture right here that we have. There's some more work that can be done. So now I'm going to go ahead and put the other parts in Navier's derivation, the other two components. Okay, so we're going to do and now we have some so I'm going to website. And this all reduces to the total derivative G. Okay, we'll have density here, and this is a gradient of pressure G plus, and then we're going to take the term of viscosity. And this is a second. If you look like this, you can see a little bit of resemblance, right? You have your x, y, z. You got your u, v, w, and this is actually a Laplacian, which is a gradient. Just a second dollar, and it's actually a view of velocity. It's pretty neat because stress depends on velocity, and force depends on the strength. Okay, and then our final body forces. And there it is. We have derived the Navier-Stokes equation. I was about to say we have derived the latest environment, but we have derived the Navier-Stokes equation. So if you could follow along the video and do this on your own, you should be proud of yourself and very happy. So now you know how fluids move and how to describe how fluids move. And yeah, so thank you guys for watching, and I'll see you guys in the next video. Thank you for watching.